So if we can think about sequences as functions, then everything that we know about limits of functions can then be applied to sequences. And the terminology and the analytic approaches are going to be really similar. So we're going to practice finding the limits of a number of these sequences, and we're going to treat them as functions. And we're going to do that to see if these sequences actually do what we call converging. In other words, we're going to say, all right, if our sequence over time as the n number of terms approaches infinity, if it looks like we're getting closer and closer to a finite value, then we can say that this sequence converges. Alternatively, if it does not look like a limit of that sequence exists, if it looks like that sequence is continuing to move to a number of different values but not settling in on a specific finite one, then we would say that this sequence diverges. In other words, if that limit doesn't exist. So let's look at a couple of examples of sequences that converge or might diverge to make a better sense of this. So let's look at this first one here. So we've got an nth rule or general rule for our a sub n terms. And we're just going to effectively look at the limit of this. We're going to look at the limit of this as we would look at the limit of a function. So if we look at the limit as n approaches infinity of this here, of this 3 plus 5n squared over n plus n squared. Initially, we might look like we're getting indeterminate form, but really think about back all the way back to the very beginning of calculus. What are we effectively saying here? We're saying that this is the same as looking at the limit, this, and if we just divide both the top and bottom terms by the highest power of n, we would have 3 over n squared plus 5. All of this 1 over n plus 1. And what do we just get here? The limit of this as n approaches infinity is just going to be equal to 5. So this particular sequence converges. As n approaches infinity, over time, as n gets larger and larger and larger, these terms are going to get closer and closer to being 5. It'll converge. We say that it converges to 5. Okay. Let's look at another one. Let's look at number 10 here. So we're going to look at the limit of this as n approaches infinity. And I'm going to rewrite this here because it'll help me see the limit of this a little bit more easily. So we got the limit of this function, 3 to the n over 7 to the n. And if we just use our power properties here, this is the same thing as saying this. 3 over 7 raised to the n power. And if we think about it that way, we would say, oh, clearly this has got to be equal to 0. As n gets larger and larger, any fraction that's less than 1 raised to an infinite power or raised to infinity power is going to get closer and closer to 0. So this also converges. Okay. I'm going to let you try a few of the other ones, but I do want to talk about numbers 13 and 14. So for this one here, we've got the limit of this as n approaches infinity, starting with 1. And we have to start with 1 and not 0 here, because otherwise we get an undefined term. And there are actually two approaches. And hopefully you can obviously see that we would be able to apply L'Hopital's rule here if we wanted to. But I want to encourage you to see if you can evaluate this limit without resorting to L'Hopital's rule. So I'll let you pause the video real quick and see if you can figure that out. And one way, if you're back, is to see if we can use the log properties. In other words, we can write this as the limit as n approaches infinity of the natural log of n all over natural log of 2 plus the natural log of n. And if you see that here, this then can be rewritten as, let me write that down here, oops. The limit as n approaches infinity and 1 over natural log of 2, natural log of n. And all I'm doing right now is just dividing everything by natural log of n. And that means this here gets closer and closer to 0. So this comes to 1 or becomes 1, right? So using log properties, I rewrote that function there and then divided both the numerator and denominator, everything by the natural log of n, which allows me to just say that my limit is 1. So this one also converges to 1, meaning over time, the terms of this sequence are going to get closer and closer to 1. This sequence converges to 1. All right, let's look at number 14 now. So if you look at the limit of this as n approaches infinity, this is a pretty easy limit to evaluate here, because if you look at the sine function as n approaches infinity, this limit simply does not exist. So fairly straightforward problem, but I wanted to show you this because it's our first example, really, spoiler alert, but it's the first example that we've had where the limit doesn't exist. Therefore, we would say that this sequence diverges. In other words, if you look at the sine function over time, if you look at the sine function as it continues to move on towards infinity, it doesn't ever settle in on a finite value. We don't get one output that appears over and over again as n approaches infinity. It's going to cycle and oscillate back and forth between -1 and 1. So this sequence, we would say, diverges. All right, try number 11 and 12 on your own if you haven't already done so, and check your solutions in the classroom. But let's briefly talk about monotonic and bounded sequences. So we talked about monotonic functions earlier in the year as functions that are entirely, I should probably say entirely non-increasing or entirely non-decreasing. In other words, the function doesn't change behavior. If you look at the function's first derivative, you would essentially say that the function's first derivative does not change signs. So if you think back to earlier in the year, that was when we first talked about monotonic sequences. So, monotonic functions. So a monotonic sequence is one that is going to continually increase or continually decrease or continually stays constant. In other words, it doesn't change from increasing to decreasing. A bounded sequence is effectively saying that there is some value n that every term is less than or equal to, and a number m, as in Mary, that every term is greater than or equal to. We are saying that this sequence is bound between these values, m and n. And kind of just in terms of the way we articulate this, we would say that the sequence is bounded above by n, meaning n is kind of like the upper boundary, if you will, or bounded below by m, meaning m is kind of like the lower bound or the floor. So let's look at a couple of sequences here, and let's determine one, if they are monotonic, and two, if they are bounded, and then let's see if we can get some conclusions from that. So looking at 3 plus -1 to the n power, let's look at the first couple of terms here. What does that look like? Well, that first term, when n is equal to 1, that's going to be 3 plus -1, which is 2. When n is equal to 2, that's going to give us +1, so 3 plus +1 is 4. And that -1 to the n is essentially just means it's going to alternate back and forth between -1 and +1. So that means our outputs are really just going to be, or our terms in our sequence are going to go back and forth between 2 and 4. Okay, so if we were to look at this being our n-axis, if you will, and just kind of looking at these, what we're effectively saying is we're going to get an output. Our first term in our sequence is going to be 2. Our second term in our sequence is going to be 4. The third term in our sequence is 2. The fourth term in our sequence is 4, and this is going to go back and forth here. So first off, is this sequence monotonic? And the answer clearly is no, it's not monotonic because we are alternating back and forth. It is not just increasing. The terms are not just continually getting larger or continually getting smaller, right? We would say that this sequence is not monotonic. It does not stay strictly increasing or strictly decreasing. Now, is this sequence bounded? Well, yeah. If we see here, we see that our lower values never go below 2. So we would say that this is bounded below by 2. And at the same time, it never gets larger than 4. So we would say that this sequence is bounded above by 4. So this sequence is bounded. Okay. So I would encourage you to pause the video and try number 16 and 17. maybe write out the next couple of terms and see whether or not these sequences are bounded and whether or not they are monotonic. Now, really quickly, let me just write the solutions here just so we have something to reference as we move on to the final part of our discussion here. But this would look something like this. And we would say that this sequence is monotonic and this sequence is bounded. Okay. For number 17, this sequence would look like this: 1/2, 4/3, 9/4, 16/5, and so on. This sequence is monotonic. It's going to continue to increase. It'll never decrease again. But this sequence is unbounded, meaning there doesn't really seem to be an upper bound or an upper limit, if you will. It just continues to increase. So looking at these three sequences here, what conclusions can we seem to, or observations can we seem to draw in regards to what we know about a sequence and whether or not it is bounded and monotonic and what that means for its convergence? So pause the video right now and kind of think about that for a moment. Well, if you've had a moment to think about that, we can say the following. We can say if, and this is kind of an important statement here that I'm about to write. So if a sequence is monotonic, we can say then it is convergent. But it is only convergent if and only if it is bounded, right? So the only sequence here that we said was convergent was number 16. This was the only sequence that was actually convergent. We would say that this sequence is convergent because we notice that it is monotonic and it is bounded. So if a sequence is monotonic and it is bounded, then it is convergent. So that's a conclusion we can draw in regards to monotonic and bounded sequences.